Hello, and welcome to this video in the Metallurgy playlist on mechanical metallurgy. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies, which stands for Welding and Joining of Materials. Additional information about my consulting business as well as training is on the web at welding-consultant.com. In this video, we're going to review mechanical metallurgy and how that affects your interpretation of the welds. We are going to look at mechanical metallurgy, which is the study of behavior of physical components under action of an applied force. So whenever you apply a force, whether internal in the weld or external, it causes some changes or deformations in the weld, and how does that affect the performance of the weld? We're going to look at elastic and plastic deformation, stress strain diagrams, hardness testing, and coefficient of thermal expansion. All these videos in this YouTube channel are made for engineering personnel who are working with welding, but may not have a direct education or training on the subject of metallurgy and welding. Let's look first at elastic deformation. Elastic deformation is deformation that is fully recovered. For example, showing it schematically on the left, there's a certain arrangement of atoms. When you apply stress, these atoms move but hold their respective positions with respect to each other. And when the stress is released, they come back to their original position. A good example would be a spring that you can compress and let it go and it comes back. So in elastic deformation, any deformation is fully recovered. So most components that we use in a daily life are operating in the elastic mode. For example, the chair that you're sitting on has to operate in the elastic mode because you don't want the chair to deform when you sit down. That won't work very well. Plastic deformation, on the other hand, is deformation that is not recovered. So if you apply enough stress to any metal or any material, at some point it can undergo so much deformation that after you release the stress, the component doesn't come back. I'm showing you this schematically over here as the atoms in the structure actually move with respect to each other and have a new position due to application of the stress. In real life, that looks like these brackets that have been deformed and bent and are in permanent deformation. So most of the mechanical processes that are used in manufacturing, such as bending, stamping, rolling, extrusion, all depend on plastic deformation because you are conducting these processes to effect a change in the size and shape of the component. One of the downsides of producing plastic deformation is work hardening. The area in the region where the deformation has happened, for example, right along the bends over here, the hardness of the material increases. And if there is repeated bending to a certain level, then the hardness can reach such a value that the component can actually break. So there is a downside to plastic deformation. Here's an example of a typical stress strain curve. We have stress on the vertical axis, strain on the horizontal axis. In the initial range of the applied stress, when you release the stress, the component comes back, and that is defined as the elastic deformation range. Once you apply enough pressure or enough stress that the component undergoes permanent deformation, that goes into the plastic zone. Even in the plastic zone, at certain point, once you apply enough stress that exceeds the tensile strength, at that point, there is permanent deformation and failure leading to the failure point or necking down to fracture. Tensile strength is a measure of the shear strength by this relation. So shear strength is about half to 0.6 of the tensile strength. And that comes in handy in doing some analysis of stress behavior of welds. The stress strain curves for different materials appears different. For ceramics, the stress goes up and there's an immediate break, so there is no deformation usually in most ceramics. Strong alloys have little bit deformation before they fail. Steels have that unusual dip in the middle before they go up and fail. And ductile metals have a long elongation before they fail. Why is that important? Because as you might recall from the cross-section, in the cross-section analysis video, we showed that in the vicinity of the weld, there are three different materials: the base material, the heat-affected zone, and the fusion zone. Each of those could have completely different behavior. For example, the base material might be fairly ductile. The fusion zone, depending on the alloy that has been added, could be behaving like a strong alloy. And the heat-affected zone might have become very brittle and could behave like a ceramic, for example. So it is very important to understand what is the mechanical behavior of these three different zones in order to correctly interpret any stress strain data that you may have from the weld. Now, it is very difficult to actually go and measure the strength of, say, the heat-affected zone or the fusion zone, because these components, often the welds are small, and it is very hard to extract a reasonable size sample, which you can put it in an instron and pull on it. So as a proxy, what we do is we measure the micro hardness of these welds and use the micro hardness or the change in the hardness across the different regions as a metric or as a measure of the strength of the weld in that location. Here's an example of such an experiment. We have welding a 304 stainless steel to a carbon steel, and you can see the weld in the middle. It's a fusion zone over here without adding any third material. So these two are just, the fusion zone is just a mixture of these two. And then we send the sample out to the lab to measure the hardness. You will notice that the hardness in the HRC scale is close to 20 in the base metal on both sides. However, the hardness in the fusion zone is close to 40, which is much higher. How does it affect the analysis? Hardness, a harder material is stronger, but at the same time, it is also susceptible to crack growth. So for example, this is a butt weld, and there is some unwelded region over here of the two components. And if this particular butt weld was flexed, then what could happen is this point over here could have high stresses, and the high stress could initiate a crack. And the crack, if this material was hard, which it is, will have a much easier time to go across the weld and lead to failure. So micro hardness testing tells us a lot about how the weld would perform in terms of strength as well as in terms of fatigue life. Another source of stress is due to coefficient of thermal expansion. Whenever we weld materials which are dissimilar, and that is quite often the case, we are welding alloys which are dissimilar. Sometimes we are also trying to make assemblies by brazing and soldering, where you have a lot of dissimilar materials in there. And a lot of these welds, joints, braze, solders are done at high temperature. And as the assembly cools down, it introduces stress in the weld just because of the difference in the CTE. Here we see a list of coefficient of thermal expansions for different materials. We start with plastics, which are about 80, go down to solders, which are about 29 or 30, aluminum, brass, stainless steel is 17, ferritic stainless steel which is 409, is 11, alumina is 8, glasses are 8. Different types of glasses have different thermal expansion. So regular glass might be 8.5, borosilicate is 3.3, and fused quartz is 0.59, which is one of the lowest in structural materials. So whenever you have an assembly where you are dealing with dissimilar materials, in a welding, bonding, soldering, brazing situation, you have to consider what are the residual stresses in the weld. Let's look at an example of a PCB, a printed circuit board. In your engineering life, I'm sure you have seen a lot of printed circuit boards, sometimes lying around in the labs, and you probably didn't think much of it. But a printed circuit board is a very difficult assembly. The printed circuit board is made of plastic, has a high thermal expansion. The copper has a thermal expansion of 17. The FR4 is 60. Solder has a value of about 30. And the device itself has, if it's a alumina, like a capacitor, has a thermal expansion of 8. So when you place all of these components in a oven, a reflow oven, for example, for soldering to take place. Now, during the soldering process, everything is fine because the solder is molten and it doesn't hold any stress. But as the circuit board comes out of the reflow oven and the solder cools down, becomes solid, and then it starts cooling down to room temperature, it introduces a lot of stress in the device and the joint. And because of the difference in thermal expansion over here in all of these components, it is not unusual to have cracks either in the solder or in the device itself. So next time you see a printed circuit board, you'll have more appreciation for the efforts required in fine-tuning the process to make sure the devices or the solder doesn't crack. On the left-hand side, I'm showing you a schematic of an assembly or a cap to a cylinder. They are dissimilar, and they've been welded on the top with a laser beam going all around the circle on the top. And when the laser is welding and the metal is molten, there is no stress. But as soon as the metal freezes and starts to cool down, it is going to introduce stress in the weld. Towards the end of the weld, the entire assembly is going to be quite hot because you are reaching the fusion or melting point of these two components. As the weld cools down, the cylinder is going to cool down differently than the cap if they are dissimilar. If the cap has higher CTE than the cylinder, then the cap will shrink more than the cylinder and the weld will be in tension. If the cap has lower CTE and the cylinder has high CTE, then when the weld cools down, it will introduce compressive stress in the weld. Now keep in mind that compressive stresses in the weld are good because compressive stresses tend to close any cracks that could potentially form. So one of the things you need to keep in mind when you design a weld or a joint or a braze or a solder, you have to consider the CTE mismatches because oftentimes you are making a dissimilar metal or a glass or a ceramic joint. In summary, it is important to know the mechanical properties of the alloy that you're welding and also the expectation of the mechanical behavior of the weld. So first and foremost, if you are the engineer dealing with this weld, go find out more about the mechanical properties of the base material that you're receiving for the welding process. And then have a good discussion with the design engineer to find out what exactly is expected from this weld. How does a design engineer expect this weld to bend or deform under action of the stress? As far as analysis, it is also a good idea to measure the hardness of the weld to look for potential failure paths for cracks. If the weld or heat affected zone is very hard, then the crack growth will be easy. Or if there are very many weak zones, for example, the welding heat might cause actually a reduction or softening of the base metal or the heat affected zone. And that soft material can cause a lot of deformation or flexing when the stress is applied to the weld. So that also may not be good. So keep in mind that the hardness gives you a clue about the life and the strength of the weld. Then you have to think about the CTE mismatches based on the orientation and the geometry of the weld or the solder or the braze joint. And you combine all of these components together, that will give you a better idea of what to expect from the weld that you have made and if any changes are required. And at that point, you should approach the design engineer and have a good discussion on which is the right way to go forward. I hope this has given you a good insight into the mechanical metallurgy, and hopefully now you know what right questions to ask in this whole process of analyzing welds. Thank you for your time. If you are interested in learning about welding and joining, please subscribe to this YouTube channel, The Weld Nugget. Videos on specific topics are in the playlist on this channel, so feel free to browse through them, and I hope you find something useful in all of those. Thank you and have a good day.